So far we've defined the electric potential for a parallel plate capacitor, a sphere, and a point charge. Well, anything else really can be built up from multiple point charges. We'll talk about a continuous charge distribution next, but let's just start with 2 point charges. So in this case, let's say I have a point over here, and I want to ask what the potential is. We get to use superposition, which just means add it up. You find the potential from one point charge, and then you find the potential from the other point charge. Note that in no way do we need to think about these point charges as interacting. We literally just get to add up the electric potential from each of them. So what that looks like is a summation over each point charge, where we have the charge of that charge over the distance from whatever our point is to that charge. So in this scenario, I would say that this is my distance, my R1, to this one, which is Q1, and then this is my distance R2 to Q2. Note that this would have a sign in it, so Q1 is actually equal to -1 nanocoulomb, and then you just add them up. Note that when we did this for electric fields, it was similar, but we had to take into account the direction, because electric field is a vector. Since electric potential is a scalar, we don't have any directions to worry about, and we literally just get to add. So this is rather straightforward. So let's think a little bit about the electric potential from a dipole. And again, what we're trying to do here is add up now the electric potential from a negative charge and a positive charge that are of equal magnitude, but now we're trying to visualize it through all space. So we have our contour map and our elevation graph. So you can imagine with our elevation graph, we could actually try to draw a line through it and just do a 1D plot as well. So something to think about in this case, we're again going to say that as the radius from each of these goes to infinity, the potential is going to 0. So we know really, really far away the potential is 0. But then as you get closer to each of these, it increases. And note that again, each of these lines should have the same increment delta V, and so they're not equally spaced. The other thing you see is that they are actually influencing near each other such that our point charge is not actually centered in this distribution. There's an asymmetry that is introduced due to the fact that there's another charge over here, right? So if I only had the positive charge, these circles would all be centered on it, but since there's a negative charge over here, that actually shifts my potential a little bit. So all of these around my negative charge, and you can see this when you look over here, this is all V less than 0. But then when I look at my positive charge, which is again this one, here we see that these are all V greater than 0, right? If you're near a positive charge, you have a large potential. If you're near a negative charge, you have a large negative potential. So what is happening at this center line? That is equal to 0. And that's this line here as well. And this is actually a symmetry line, right? That everything is symmetric along that line in kind of a rotation sort of way, positive versus negative. And the other thing to notice is that line can go all the way to infinity since the potential at infinity is 0. So I hope that this visualization makes a little bit of sense. Again, understanding how charges add together is really important. You can think about what this is going to look like if you have 2 positive charges. You won't then have a V equals 0 line there, since you would have positive potential on each side. So adding charges together is fairly straightforward as long as you understand these different representations and how the electric potential looks like for a point charge.